in the meanwhile, maybe I can also start talking a bit. So maybe just about my background. Since I'm new in the round, I originally studied physics, but then I moved into atomistic simulations of materials, um, and more software engineering as well. So first was in academia, um, doing things like workflow managers for large-scale simulations. Um, and then later at Microsoft, where I worked in the quantum team on a cloud platform for atomistic simulations.
Wow, very good. And now you
Yeah,
should be able to share your screen. So you are the
fantastic.
host.
And yes, I think I can share the screen now. And
So
so can you see my screen?
yes.
Fantastic. So I will start the presentation.
Yes.
So
I interrupt you when you're saying you worked with Microsoft on.
yes, yeah. So since 2024, so since roughly 2 years now, I'm so-called head of computational materials engineering at SCHOTT. That means I lead a small group within the materials development, and our goal is to use computers to predict materials properties and help our materials engineers be faster in making great materials, and then also seeing how these materials enter production and eventually the real world. So that's what I love about this position. And I will start by talking a little bit about what we do in SCHOTT and also in the group, and then we'll focus on this GlasAgent project, where basically the idea is what are the building blocks that we need in specialty glass development in, let's say, the agentic era. And yeah, lots of time for discussion, but feel free also to interrupt me. I think we have a small crowd and we have enough time. So about SCHOTT, we are a specialty glass maker headquartered in Mainz, but with around 17,000 employees around the world. So spread all over the world in terms of production, in terms of research and development. We have centers in North America and in China. One peculiar thing about SCHOTT is that SCHOTT is 100% owned by the Carl Zeiss Foundation, and the profit that SCHOTT makes that goes to the foundation is then used to promote the sciences in the German states that the foundation is active in, to fund things like professorships, prizes, student projects, and so on. And so SCHOTT is really a materials company. So we don't sell a machine that has some piece of glass in it somewhere. We sell the glass, and we are a specialty glass company, and that means we don't sell, let's say, wine glasses or architectural glass, but glasses where there are kind of special demands on their properties. And so SCHOTT started as basically the glass laboratory for the microscopes of Carl Zeiss. At that point, the challenge was that you wanted to get rid of the so-called secondary spectrum in the microscopes. You want to focus the light of all different wavelengths on one point, and of course the refractive index depends on the wavelength, and so you needed to find glasses to be able to compensate for this effect, and that's how SCHOTT got started. We also, so in the case of pharma packaging, the special property is not dependence of refractive index and wavelength, but things like chemical resistivity. You want the medicine in the vial to be able to stand on the shelf for tens of years and not be contaminated, and of course also mechanical properties, because you don't want them to break if they fall down. Glass ceramics are another really interesting material. So there you first make a glass, and then you seed inside this glass a crystalline phase with negative thermal expansion. And you try to balance the amount of the negative expanding crystalline phase and the remaining positively expanding glass phase in such a way that they add up to exactly 0 thermal expansion. So there's different variants of that. One is for your cooktop. Maybe you know it from home, where you need to be able to have, say, 600 degrees on one place and 0, like room temperature, very close to it, and you don't want it to crack. But then there's other applications like in space, where you have like the sun that makes the thing very hot, and then it comes back into the shadow again. The newer topics are this ultra-thin glass, foldable glass that enables the smartphones that are foldable smartphones that are coming out now. What's foldable it's all bending with a very small radius, so you should not say foldable. And then, for example, the augmented reality glasses that are coming out now, there the challenge is that you want to marry a very high refractive index, because that defines the field of view in your augmented reality glass with low density. The reason why we don't have these glasses already is because what people have been able to engineer so far is too heavy, that people want to wear them for a day. And so the latest generation, they think they can finally crack that, but every gram counts. And so you want to kind of, you need to combine these two properties, which typically go against each other. And this is the kind of materials optimization problem that we try to solve at SHOT. And there's hundreds of glasses, or even if you're just talking about the optical glass catalog of SHOT, there's hundreds of glasses in them. And that means glass development at SHOT is never static. So we are always in the process of developing new glasses, and we need to stay competitive. And so we want to use computers to help us become faster. And so what do we do so far? So on the one hand, the kind of computational tools we have are semi-empirical property models that tell us for this composition, if you go in this direction, this property should change in that way. These are typical like simple analytical formulas with a few coefficients that may be fitted to experimental data. People have been doing these for decades. There are very many of these models, and they are useful if you know the limitations. I mean, they are simple, so they have limitations, but if you're aware of them, they're useful. On the other hand, you have the kind of fully data-driven models, where if you have enough high-quality, consistent data for a given property, you can build, you can use these vastly more flexible models to also gain substantially higher accuracy. And so both of these, of course, continue. There's also the atomistic models, and then, of course, Hongmin started this series, so I guess there's some skew towards atomistic people also in the crowd. In glass modeling, modeling glass atomistically is hard, and there are different reasons for that. So on the one hand, glass is an amorphous material, so that means you need a large simulation box. Also, glass is not in thermal equilibrium. So what you see here on the left is that if you come from the liquid phase and then you cool down, if you cool down fast, you will get a larger volume than if you cool slowly. So if this liquid has more time to relax. So in the end, this means the properties of the glass that you use that you compute depend on the cooling rate. Of course, computationally, we are limited to cooling rates that are somewhere close to the speed of atomic vibrations that we need to resolve. So that's a big challenge. And then there's a third challenge, which is that the types of glasses that SHOT produces, they have lots of different chemical elements in them. And then, of course, across the SHOT catalog, we have even many, many more elements. And so you need potentials that are able to model this breadth of chemical space accurately. And that used to be a really big challenge once we still had to make all of these potentials by hand. But with things like universal machine learning and atomic potentials, we think we're making real progress in this. And then, of course, there's language models that have many uses in R&D. But today I would now like to focus on one particular use case, which is to use these language models to make a variety of different tools that we have in specialty glass development, digital tools, more easily accessible. And that's one of the topics in the GlasAgent project. So Project GlasAgent, very briefly, it's a Material Digital 3 project funded by the Federal Ministry for Research, Technology and Space. And we work together with 9 other excellent partners. So that's companies, research institutes, universities, focusing on 2 main goals. So one overarching goal is to accelerate the development of specialty glass, and the other goal is to enable the recycling of specialty glass. Today, we are focusing on goal 1. So in goal 1, we are doing lots of experimental development as well. So you can see a robotic melting system, automating sample preparation, doing method development, switching to faster methods from slower methods, and so on. But here I'll talk a bit about the chatbot that we're developing, and then also the automation of simulation workflows. So how does this chatbot that I'm talking about, so how does this work? So the idea is there's a glass developer at Shot, and they open their browser and they log into a chatbot, and that chatbot is powered by a large language model, and it has access to a range of tools. So it can search in glass databases. It can use these models that I showed before to predict the glass properties based on composition. It can also do so-called calculation of phase diagrams. So there's commercial software for doing thermodynamic calculations based on commercial databases. It should be able to run atomistic simulations. And in the project, there's also a robotic melt at the Bundesanstalt für Materialprüfung, Berlin. And so it can submit melt requests to this robotic melt. And so in all of this, we work with the University of Jena to ontologically decorate these requests so they are kind of understandable from a machine point of view. So when the project started, I basically started with mocking up some chat that I thought if we managed to reach all of the project goals, that should be possible to have with our chatbot. It's called Otto, after Otto Schott, the founder of our company. And so within the project, we are also developing a new glass. It will be a new glass for like direct pressing of lenses, where we want to adapt it to the properties of the pressing tools that they have. And so this then is, for this, in the beginning, we'll be looking for a certain refractive index, a certain Abbe number, and a certain coefficient of thermal expansion. And then Otto should be able to start searching in databases, and then the conversation continues from there. And I show a first example here. We did an integration with a database called SciGlass Next. That's a database hosted at the University of Jena. It's free. It's the largest free and open database for glass properties. Anybody can register there and check it out. They have a great user interface, but it now also has a model context protocol endpoint, and that's what we connect to with the chatbot. So I can say I'm looking for this glass with these properties. And in particular here, for example, I'm not using a unit. Just say CTE 4.5. And so it knows at Shot we mean ppm per Kelvin in that case. And then it finds the corresponding field in this database. It figures out, okay, they're using a different unit. I can check exactly what kind of request the tool has sent to the database. And then I can look at the result in JSON form, which is the form that the database returns the result, but I can also download it in Excel form. And if you ever move into, or if you're already in industrial modeling, or if you ever move into industrial modeling, Excel is a very important tool here. So so far about the searching, but now We can also start using the data-driven models. So these you start with the glass composition, and they can predict properties. And so let's have a look at what I can say here. So I can say, how do the properties of the last glass compare against ML predictions? This is also still using this public model from SciGlass Next. It's a model called GlassNet, developed by Daniel Cassar. So here I see how the prediction and the measurement from the database differ. And now I can use this as a starting point for exploration of material space. So I could now, I can increase the percentage of a given component, see how the values change, and use this to help me with developing a new glass with the target properties I'm looking for. Now coming to the atomistic simulations, what I'm actually talking about here. So in order to make a glass in the computer, you really just throw all of the elements that your glass contains in a big box. You heat it up to very high temperature to melt it, and then you cool it down again. And so once you have cooled it down, you have the glass structure. You can start analyzing the glass structure itself for things like radial distribution functions or properties of the, for example, ring statistics of the glass network. And you can start computing properties like elastic constants, coefficient of thermal expansion, and so on. And typically, this type of workflow was, so there's a researcher, maybe glass developer, who says, oh, I have a problem here where my atomistic simulations might help. And then they write to a simulation expert. And once the simulation expert has time, they will look at it, and then they say, oh, okay, so maybe this is interesting. We should make a project. We should have a budget, and then this project maybe can start at this. I will have time capacity at this point in time, and then at some point they have time. They start submitting the calculation. Hopefully they didn't make any mistakes. And so at some point later, when the calculation is finished, they look back, they start writing a report, and then it comes back to the original researcher. And so this kind of process, in the very best case, I would say it takes something like a week, but it can easily take months as well. And so that is simply not fast enough for atomistic simulations becoming a routine part of glass development. And so what we're doing in the GlasAgent project together with the BAM and the Max Planck Institute for Sustainable Materials. So this is with the group of Tilman Hickel at BAM and Jan Janssen at the Max Planck Institute. We are developing workflows for automating this process. And so let's have a look at how this works. So you can say to the agent, okay, so now I've arrived at the glass composition that looks interesting and that I might want to melt, but I can in parallel also say, I am interested in the atomic structure of this glass. Can you calculate it for me? Since it is an expensive operation, it has a cache, and it will check actually whether the simulation is already present in the cache. If it's not, you can say, yes, let's start the calculation. And so you will get a kind of a visualization link at the end that once the simulation is finished, you can click on it and look at the results. And this is roughly what it looks like. So you get a view of the glass structure that you have created. So you can, if you're interested in like a look at the environments of individual ions in the glass structure to see whether that fits with your intuition. You can look at the structural, like statistical structural analysis, meaning these, what I said, radial distribution function or ring statistics, structure factors, and so on, that are computed for this glass structure. And then look at properties like high temperature, viscosity, coefficient of thermal expansion, elastic properties, and so on. And let me move further. And so actually, so the package that is behind this, meaning both the workflows and also the web API that we are talking to from the chatbot. We have made it open source. It's called Amorphous Pi. And if you're interested in glass simulations, you're very welcome to check it out. It's still under active development, but I expect that we will converge somewhat towards the end of the year. So far, this effort has focused on classical potentials, but the next step for us will be to move to machine learning intertopic potentials here. And just for completeness, so there's also, I mentioned Kalfat modeling. We are doing this together with a company called GTT Technologies. And here the idea is we start making these types of calculations available from the chatbot. And so one thing I can say, for example, is I would like to see the liquidus temperature between silica and a typical soda lime glass. So you add the soda and lime in order to lower the liquidus temperature, and so well, okay, so it asks so to tell it which units to use in this case, and it will give you a kind of a one-dimensional line going from 0, which is like the silica, to 1.0, which is in this case the soda lime composition that the LLM in this case dreamed up. So again, so this composition here is something that the LLM pulled out of the hat because we didn't tell it what to do, but everything else, so meaning the calculation, the modeling, that happens in the background using the tools, and the LLM is just presenting it again to us in the chat. It's not doing any modeling itself. And so that's already my conclusion. So in the GlasAgent projects, we're using the large language model to incorporate lots of different tools that we have for helping in glass development. I showed only a selection of those, but there are many more. And basically, if I had to create a graphical user interface for bringing all of this together, it would be completely unusable. So my goal is to use language models and the kind of the very compact way how we can express request for simulation or data to make it possible to have a one entry point that goes to a very wide variety of tools and bring those together under one hood. And then the second is that we're working on integrating atomistic simulations and also these Kalfat calculations into the glass development workflow by making them easily accessible through the chatbot interface by automating the simulation workflows. Great. So I think we have lots of time for discussion, and I welcome your questions.
Wonderful. Thank you very much for this very nice presentation, very practical presentation, so we can all really see the magic of artificial intelligence tools. Now, together with Tang Jiangka, the PhD student of Hongping Tang, I will now lead the discussion. So if you have any question, please raise your hand. I hope you can open your microphone, but maybe let me start with one question. You mentioned ChatGPT, you mentioned Claude, you mentioned that it might be expensive, but then you were saying that actually Sciclass Next is open source and free. So how does now the components of the frontier models where you have to pay and the open source model, how does that interconnect?
Did I mention that it was expensive?
Yeah. I think once you said you have a cache, so therefore you can see what you paid for. And
yes.
I know that people saying if you work with Anthropic is great,
right.
But it's not,
yes.
not cheap. It's not inexpensive.
Yeah, sorry, I should have been more clear. So thanks for the opportunity to clarify that. When I said that there's a cache, I was talking about these atomistic simulations. And what I mean by expensive is, in the end, running an atomistic simulation workflow for a glass will take a day, and it will take a number of cores to do that. So that's what I meant by expensive. Of course, you also pay for the large language models themselves. And it is actually true that, let's say, if you do it in a naive way, as we still do, and you send the information of all of these different tools with your interactions with the LLM to the API, that can get a bit expensive. I do expect, though, that the price for this will come down very fast, because it's at the moment, at least, we're using the LLM in a relatively, I mean, it's not a super difficult task. It requires some context as to do this translation of the request of the class developer into the machine language of the API, but that's all the LLM has to do here. And so over the next month, I expect that more and more the lower tier of LLM models will be sufficient to do that. So if you go back 1 year ago, even just selecting from a set of 15 documented tools would have been a challenge for the LLMs. That is no longer the case, but extrapolating from that, I think it will get quite cheap, and we don't need to worry about the cost of the LLMs in that regard.
Very good. And I learned, I think, and Hongbing will also test this, that we have now this open source LLMs from China, which you really
Right.
download on your own computer and totally unconnected with other country can work on this. Maybe we should hurry up in testing this, because I also read that China might to hinder that know-how of China
Right.
way to other countries. So we are at the moment in a super dynamic way. But I understand from Hongbing, it's good that he said at the World Artificial Intelligence Conference that he will discuss all these things, because I'm quite often listening to Peter Diamandis' moonshot videos, which I think are really perfect. And therefore, clever people are discussing on the new model development. And there, for example, discussing to have a hybrid model to use this not so first class Chinese open source models, to have it on premises where you don't need to pay cost. And then, of course, you can verify the results with the more expensive frontier models.
Yes, I mean, you can use open source models as well. There's, of course, by the way, not just Chinese open source models, but I mean, there's also very good models from Meta and so on, right?
Ah, yes.
But I mean, at the moment, we don't feel the need yet. And eventually, if you want to run a really good open source model, it's also going to get expensive, just because the size will be large, and it's much more difficult to kind of amortize the cost of running such a model if you have a much lower number of users. So the way the economics works is that yes, you can run a really big model if you have very large numbers of users, right? And you can batch together all of the requests. So there's some trade-off there.
Okay. Tang, do you have a question, or does any else want to raise a question?
Yes, I have a question. Thank you for the insightful talk. So since you mentioned the digital twins, so I have a question about digital twins. So in industry, how do you actually build the digital twin model, and how to connect the digital twin model in the cyber physical worlds in the real worlds?
Yeah, I mean, I'm not sure I'm the best person to talk about this topic, because I mean, digital twins is typically you're talking about something like a factory, right? Where you say you want
Yes.
to have a like a complete digital model of the factory, and instead of changing like turning one knob in the factory, you first want to turn the knob in the digital model and see what happens, and then do it in the real world. I mean, for materials. I mean, basically, the more simulation we do routinely on the materials, we
Uh-huh.
automatically build up a kind of digital version of what we are working with. So, I mean, in that sense, we are building a digital twin here of the glasses. But this is only the case once this is really completely routine. So every glass development is accompanied by atomistic simulations. Also, once I mean, also the digital twins are only as useful as accurate they are, right? So
Yeah.
they're especially for atomistic glass simulations, I think there's still still quite a lot for us to do. I mean, we are doing it, and we'll actually also be hosting next year the technical committee for atomistic simulations of the ICG, that's the International Commission of Glass, at SCHOTT, and so there will be all of the world-leading glass modelers here. We discuss current issues, and we do that every 2 years. Yeah, there are some hard problems in terms of accuracy as well.
Okay, thank you. And any other questions?
Can the others unmute your microphone or raise your hand? Maybe then before you consider a question, I have another question. You mentioned recycling, and now from your presentation, it got clear for me that recycling indeed is a challenge. So what is the challenge of recycling? I think the challenge is that glass consists of a number of elements. And how does recycling work? Do you just remelt and then adjust, or can you get the elements down? Can you separate the elements? Or
Yeah. So of course, container glass is one of the examples where, at least in Europe, where recycling actually works. It's not the case all across the world, but in Europe it's true. For specialty glass, so far that's very difficult because you have much higher hurdles, specifications for what can go into your glass. And so in order to be able to recycle specialty glass, either you can directly get recycled material from a very clean source, which is one option that is, of course, also being investigated. But the other would be that you can find some way to separate even different specialty glasses from each other. And that is one question that we are addressing in this project together with a company called Praltec, who have is the world leader in some of these types of separation machines, and they can do density-based separation with very high precision. Yeah, so high that we think we can even separate different specialty glasses from each other.
sounds very interesting. What happened if you have specialty glass in your container glass? Is that harmful? Could this special dopants be harmful in container glass?
It depends always, of course, on how much you have in there. I mean, we're talking about very different volumes here than container glass. I mean, to me, that's from a R&D perspective, I think that's what makes specialty glass so interesting, is that we are talking about, so that there are some products that we produce with very high volume, like the pharma packaging, where let's say most of the world's COVID vaccines are shipped around in these shot vials, or the Ceran cooktops, which of course large volumes, but there's also lots of different glasses at SCHOTT that are produced at quite low volumes, and so that means yeah, there's this breadth of the portfolio, and makes it also much easier to change something than if there's not like billions of dollar already invested in like a huge production series. Yeah, but yeah, for recycling, we'll have to see. We're taking the first steps. Of course, for recycling, you actually want volume, so we have to start with the ones that have a larger volume. We have to figure out all of the contaminants, how important they are for the specialty glass, where specialty glass contamination can be even more problematic, especially if you're talking about pharma, where that is very highly regulated. So there are challenges there, but we are working on them.
And the window glass, is this window glass similar than container glass, what we have in our buildings?
I mean, I'm not an expert on it, so I shouldn't comment, but to my understanding, yes, it's relatively similar, yes. Of course, for window glass, you care much more about transparency.
And
So,
there's coatings, sometimes even some silver coatings on this window glass.
and you have coatings, anti-reflective, whatever. Yeah, you have so it would be wrong to say that this is not a glass where where also so even in window glass, in the end you will have very high demands on certain properties, but in the end, specialty glass in a way is even, at least in my understanding, about scale. So it's like if something has become commodity, it's like a huge available at huge scale, then maybe for a company like Schott, it's time to look at something new.
Thank you. More questions? Tang or the others?
Hello, can you hear me?
Yes.
Yes.
Hi, thank you for your nice talk. I just want to ask about like the LLMs. They are usually not very trustworthy. So there could be like cases of hallucinations.
Mm.
So how do you handle hallucinations? Because like the output is not really deterministic in LLM. So
Yeah, so these are two different things, right? So one is hallucinations, and then the other is determinism. So yeah, I mean hallucinations. At the moment, we don't have like an automated. So one thing you can do, right, is after you have received a message, you can have another LLM or another loop that checks whether there's any hallucinations in the output. I have to say that so far, I haven't come across significant cases of hallucinations in the let's say the copying of the numbers, which is basically happening for doing the for translating the user requests into the API calls. I would say we are just at the point where we're starting to get users on board, and so we will do a more systematic screening of that and what is the percentage of where this happens, if it's 0.1% or it's 1% or even more. My feeling is that the LLMs have gotten very good in this, at least if it's not so depending always on the type of question you ask. But for these type of questions where it's really about translate what I write here into a tool call, that the number or the percentage of hallucinations has really gone down a lot. That said, one should still check it. In terms of non-determinism, that is true, of course. So if I ask the same question today, and if I ask it again tomorrow, I will get a slightly different answer, and we'll see. I mean, whether people get comfortable with this or whether people will not be happy about this. So one thing I can mention is that in the end, we are just talking about translating between human language and the machine language here. And so you can always check exactly what request was sent to the tool and exactly what came out. Also, if you're talking about these database searches, in the end, the Excel file that I showed, this is not processed by an LLM. This is just taking the response that came from the database and directly converting it into that format. So there are points in this where you don't actually rely on the LLM not making a single mistake. Let's say, for example, if it was in a very long list of glasses that come out of the database query. But there are points where it might play a role, and so we still have to systematically evaluate it.
From which organization are you, Surey?
I'm from GNU Gießen.
From?
Gießen University.
Gießen. Very good. Okay.
Yeah.
Justus Liebig University. Okay.
Yeah.
Any more questions, comments? Then obviously everything was glasklar. Glasklar würde man im Deutschen sagen. Übersetzt.
Yes. Yeah. I mean, One thing you maybe to keep in mind is so so far I think so Hongmin has thought about whom to invite to the series. I've also made some suggestions in the past, but if you have some suggestions of people you would like to hear, I think that's something that you can either tell us now if you have some great suggestions, or you can write to Hongmin.
We have at the moment 7 more
Mhm.
areas announced in the webpage, as I said, materials-valley.de. And there you see we have dates till the last one is at the moment on 17th of December. So as Leopold says, there are still some dots, some vacant slots in between when we continue every 2 weeks. And I think the next one is at the moment on 30th of July. So in 2 weeks, we have small features, big impact, designing at the micro scale with generative AI from Samuel J. Cooper.
All right.
And you can register. And as you know, if you register, then you get the link. Good. And by this, I will first of all stop the presentation. And if there's no further comment, I would say thank you very much. Thank you very much for this nice talk. It was very practical, very illustrative to see how really in life the world is changing. You have now a new colleague, artificial intelligence, a new colleague, which is in your group, and treat also this colleague as well as you should treat all other colleagues. Now the clapping hands are coming. Thank you very much, and have a good evening, and bye-bye till next time.
Ciao,
All right,
Andres. Ciao,
thank you.
everyone.
Leopold, wenn Sie ganz kurz mal drin bleiben,
Mhm.
das wäre nett.
We might want to stop the recording.
I stopped already. Stopped already? Okay, I think the others. Ich habe auch
I still see the recording.